Hi everyone, and welcome to another unit in AP Calculus. Today we're going to introduce the idea of area under a curve and how it relates to the calculus we've learned so far. But first, let's go ahead and talk about just a simple problem here, one that may be from our elementary days. And we have a train traveling at a constant speed of 60 miles per hour over a period of 4 hours. And we want to know what distance did this train cover? Now, you might be familiar with the equation distance equals rate times time, but where did that come from? And how is moving into this discussion of area going to relate to using a rate to find the distance covered? So if we look at this graph here, this blue line represents the motion of the train. So we're traveling at a constant speed. A constant speed is that horizontal blue line. And if we wanted to know the distance that the train covered, the easiest thing to do would be to take and multiply the rate times the time. But in reality, if we relate it to the graph, because remember, we've got more than one way to talk about things that are happening in the world mathematically. We can make a list of numbers, we call that a table. We can put it in terms of an equation, that would be the distance equals rate times time, or we can draw a graph and look at it graphically, and that would be the picture representation of mathematical things that are happening. So if I draw a line here and cut off the first 4 hours, we have a rectangle. And really, this side of our rectangle is our rate. That's our y value, right? So y equals our rate. That's the 60 miles per hour. And then this along the bottom is our time, and this represents the 4 hours. And so you can see that distance equals rate times time, yes, holds true. However, when we look at the graph, we need to understand that when we do distance equals rate times time, really what we're doing is we're finding the area under this curve. The area that the curve represents, or the area under this curve, represents the total distance that this train covered. So the distance is 60 times 4, or 240 miles. So let's kind of like sum this up just a smidge here. When we had a curve that represented the rate, so if we are given a curve representing a rate, the area underneath shows the total amount of change that we see happening with whatever that rate is measuring. So the area underneath shows the amount of change. Here, if our rate is miles per hour, so here our rate was miles per hour, then the area represents the total amount of change in those miles given that rate. So that's what we have going on here, and that's kind of an introduction into what Chapter 5 is all about. So now that we kind of are starting to understand this idea that when we have a velocity curve, or a curve that represents a rate of change like miles per hour, it doesn't have to be velocity, the area underneath represents the amount of change in whatever the rate is measuring. Here, anytime we're given a velocity curve, the area under that velocity curve will represent the distance that the object has traveled. So suppose we have a train that's not traveling at a constant rate. Suppose our train starts at a velocity of 0, so let's go ahead and sketch this curve, and accelerates to a velocity of 60 over the first hour. So we're going to call this little spot 60. Then it is a constant 60 miles per hour over the next 2 hours, and then slows down, which we're going to assume that it's going to slow down in this linear fashion, to a rate that is 0, so it comes back to a stop. So if this is my velocity curve, you'll see that it's no longer a rectangle, but now it's a trapezoid. And so we have different ways that we can break this trapezoid up. We can make it into, a trapezoid, or we can break it into 2 triangles and find the area of each triangle and then add it with the rectangle. But the idea is the area under this trapezoid is going to represent the distance that the train covered. So let's go ahead and use the area of a trapezoid. The area of a trapezoid is 1/2 the height times b1 plus b2. So here, we'll call this b1 since it's on the top part. It is 2 hours. Base 2 is 4 hours. And then the height is 60. So the area under this curve is 1/2 times 60 times 2 plus 4. And when we crank it out, we get a distance of 180 miles. So again, the concept, the big picture here so far is that the area under a rate gives you the amount of change. If the rate is velocity, then the area represents the distance you covered during that period of time. Now, what if instead of being given a graph where we have a curve and it's a geometric shape, what if our information is in a table form? It's a list of numbers. Well, we can follow kind of the same idea here by breaking it up into geometric shapes. So the first thing I would do is I would start out and I would plot each of these data points. And once we see that we have everything plotted, what we would understand is that this is what we call discrete data. Discrete data is little bits and pieces of data points. And what we do is we kind of make an assumption here that it's actually a continuous scenario. The train is constantly in motion. There's no, jerks. It doesn't disappear or stop and then jump to 60 miles per hour randomly. So we can kind of assume that this curve probably follows some sort of shape like this, where we had some deceleration and things like that. But it probably follows this smoother curve than, just connecting them with lines. But the idea here is what happens when we take this area, and if we take our data points and kind of divide it up, if we were to find, a shape to fit in each area, we could split this up into like 4 different shapes. Like, for example, you might want to use a triangle here with this little first trunk. Or you might want to use, this is sort of trapezoidal here. You could almost use a little trapezoid here. You could almost use a little trapezoid here. But the idea is we could maybe estimate the distance covered. I don't know that we could get it in a precise exact value here. But the idea is we're going to take this curve and we're going to do our best to estimate the distance covered given these little data points. Because in reality, when you're given data points, being able to find a precise answer is very rarely what happens. More often than not, we estimate and we want to get within a certain amount of estimation. So the more data we have, the better our estimate. Here, our data, it's okay. We would be able to estimate by breaking this up and finding the heights of the trapezoids, right? So here it's like the trapezoid is on its base. So it's almost like it's flipped up. So you'd have B1 here and B2 over here, and then the height would be the time. The height would have to be the hour. So we take that trapezoid, and especially compared to the one we just did, the trapezoid would be on its side. So that would be a way that we would evaluate this sort of a scenario, is we'd use little trapezoidal shapes. Now, that's actually a lesson we're going to learn later on in Chapter 5. But for now, what I want us to understand is that we can partition, that's the word that we're going to see thrown around, we can partition or slice up a curve and use geometric shapes to estimate the total amount of change, or in this case, if it's a velocity curve, the distance we travel. So if you have a velocity that looks like this, you would want to do the same thing. You'd have to figure out, okay, well, I need some data points, and I would drop little lines down, and I'd partition, and I'd slice. And one of the really common and easy ways to slice up a curve is, instead of using triangles or trapezoids, just using a really basic shape like a rectangle. And so if we can take this curve, and especially if we have an equation, so suppose this is some sort of function that's, some velocity function, we have an equation to represent this, well, we can actually find any of the y values on the curve. It's not the same case when you have data here. Data, you're just going to use the points you have. But if we had an equation, we could figure some things out. And instead of using just 4 little rectangles, we could partition it even more. My lines are very crooked. And the more rectangles we can use to partition, the more little slices, then, we're going to find like 20 different rectangles and just add the 20 little areas together. And so the idea is, if we can take and turn these into rectangles, some of the rectangles will be, a little bit above what's happening. Some of the rectangles will be a little below, depending on, whether my graph is increasing or decreasing or, that sort of a thing. But the idea is, if I add these rectangles up and find the area of like 20 rectangles over this little period of time, I can get an even more accurate estimation of the distance that my train in this case has covered. So the idea here is partitions, the idea is rectangles. And this actually has a name. We call them rectangular approximation methods. And when we're talking about rectangular approximation methods, we're partitioning our functions into rectangles. We've got a couple different ways we could do it. And let me see if I can kind of show you a couple of the different ways. First of all, we have what's called a left rectangle approximation. And for this, I'm just going to draw a really basic curve. I'm going to draw a little parabola. And what a left rectangle approximation would look like is we would have various little partitions for x. So let's just say 1, 2, 3, 4 here. And if you partition, we're just going to keep it simple and just do 4 partitions. And if I draw 4 rectangles, 4 partitions, a left rectangle approximation uses the left side as the height. So here, right here on the left side, this first rectangle would have the left side of the rectangle being the height, which means part of the rectangle is going to overestimate. The next rectangle, I would be using this y value, and I would draw this rectangle, and I'd find that area using the y as my height, and then the base would just be the distance along the x. Here in this case, you know, one side would be 1, and then whatever the height, that would be the y value of the function. I'd have to plug some numbers in and get y. So over here, for this middle one, we'll draw it in purple. I'm going to shade it. So again, one side, because remember it's length times width, right? We call the width is what we usually refer to as along the x-axis, but here the widths are all 1. Okay, so it's really nice when the widths are all the same because it's just 1. And then here along the side, this would be my height. My y would be the height. And then you'd have one more rectangle here on the other side that actually would have the same height as the purple triangle or purple rectangle. And here you'd be underestimating on this little chunk, but the idea is some places you overestimate, some places you underestimate, and it all kind of balances out. So this is the idea of how to draw LRAM or left rectangle approximation methods. Another way that we can draw rectangles is instead of using the left side as my height, I can also use my right side as the height. So here we call this RRAM, right rectangle approximation method. So it uses the right side as the height. So again, if I draw a nice simple curve, we'll draw another parabola here. It's nice and easy. 1, 2, 3, 4. And if I draw my little partitions up, so I always start, and most of the problems I give you will tell you how many partitions. It would be nice if I could spell partitions. In other words, we're going to draw 4 rectangles. 4 little subdivisions. So we've got 1, 2, 3, 4. Those are my 4 partitions, if that was at all confusing to you when we did LRAM. So here are my 4 partitions. It starts the same as LRAM. They all start the same, but it's just a matter of where do I draw the top. So here, my first rectangle, I'm going to go to the right side of the interval, and I'm going to draw, this is my rectangle. This is my RRAM rectangle. So I still have one side is 1, right? So that would be my width. And then the height is still y, but it's this y value, not the other side. So let me zoom out and show you the difference, because it's the same curve, but if you'll notice, LRAM has a taller rectangle because it uses the left side of the curve as its height. RRAM, it's the same partition, but we're drawing the top of the rectangle from the right. Okay, so are we going from the left or the right? That's the idea here, is when we draw our rectangles, that's how we do it. So when we draw these RRAM rectangles, we're going to go to the right side and use that. So the right side, okay, and then the right side. And what's interesting is sometimes, depending on your curve, sometimes if your curve starts at 0, LRAM is often, the first triangle can often be like having no height. So it can be an area of 0 if your function starts at 0, that sort of a thing. So we can draw our, the top of our, we can cap off our rectangle from the left-hand side of the curve, from the right-hand side of the curve, and then the last type of rectangular approximation is called the midpoint approximation method. So MRAM, so LRAM, RRAM, and MRAM. And MRAM would look like this. If I have my function here, 1, 2, 3, 4, I'm going to still draw my partitions the same way. They all start the same, right? 4 partitions. You just draw them where, you divide it into the 4 equal little sections here. But then MRAM requires us to find the midpoint. So here, this x value would be 0.5. So I would have to do a little bit of work here because the height here, the height is going to be f of 0.5. So when we look back at MRAM that RRAM and LRAM here, the height was f of 1. Here in LRAM, the height was f of 0. So it really depends. It makes a difference. The y value is always going to be the height of your rectangle. It's just in LRAM, it's using a different one. We draw our rectangles differently. RRAM has a different value, and then MRAM has a different value altogether, with being the midpoint. And so you kind of have to do a little bit of work to find those midpoints. So let's finish drawing in some of our midpoints here. So remember here, this would be 1.5, so the height would be f of 1.5. The next triangle would be right here, or sorry, triangle, the next rectangle would be here, and the height would be f of 2.5, because that is the x value of the midpoint. And then last but not least, you would have a final rectangle right here, 3.5, and so that would be the height. So somewhere in the middle, it's like that baby bear, mama bear, papa bear, right? So, everybody, complains one is too hot, one is too cold, and baby bear's porridge was just right. Well, this is baby bear's porridge. It's just right. It's not too hot, it's not too cold. And MRAM tends to be a little bit more accurate compared to LRAM and RRAM. But really, it depends on whether the function is increasing or decreasing. And I never remember how to say whether it's going to be an overestimate or an underestimate. And MRAM deals with a concavity. And we'll talk a little bit more about that as we move forward. But here, LRAM will always be too high, will always overestimate when that function is decreasing. It's an underestimate when f of x increases. Now, I always have to draw the picture. I am not good at memorizing stuff. I've never claimed to be a great memorizer. I just draw a parabola, and I draw LRAM, RRAM, and MRAM and say, oh yeah, which one's which? Well, RRAM is the opposite. RRAM is an underestimate when f is decreasing. It's an overestimate when f is increasing. And it's really important to know this and be able to draw the picture and distinguish that, because on the AP exam, oftentimes on a free response, they'll ask you to do a rectangular approximation method like LRAM or RRAM, and they'll ask you if it's an overestimate or an underestimate, and you'll have to go back and it's going to tell you somewhere in the problem that the function was increasing or decreasing. And because you know that, or it might say, it might sneak it in and say, well, the derivative is positive, which would indicate that the function is increasing. So you kind of have to weed through the information. They'll always give it to you. You just have to find it and use it. So knowing, how to draw this and say, well, my justification, I know it's an overestimate, but you have to say it's an overestimate. If you're using RRAM, the justification is it's an overestimate because the function is increasing. In the same way that when we justify a max or a min, we're looking for specific language. Same thing here. You need to use specific language and refer to the function being increasing or decreasing. We're going to learn some more approximation methods throughout chapter 4 or chapter 5 here, and one of the other justifications for being an over or underestimate using some of these other methods, it deals with the concavity. So we're really going to have to nail that down, and that is something we need to remember and memorize. You know, is it increasing or decreasing, or is it the concavity that's my justification? And that'll come with time, and we'll kind of sum it up and find a way to make sure that you guys are solid on that. But let's go ahead and do a little example here and see how this rectangle approximation method is going to work. Now, the first thing we need to do anytime we're given a function, we actually need to go ahead and graph this function. So I'm actually going to graph the function 3 times, and we're going to take a look at what the LRAM, MRAM, and RRAM will look like for this function. So let's go ahead and graph it. So let's go ahead and do some partitioning now that we have it all graphed. For MRAM, our partition would look like this. We would literally come here to the right in the middle at 0.5, and this is where we would draw our first rectangle. Now our second rectangle would be between 1 and 2, and we would have this midpoint here. And when we draw our rectangles in, it looks like this. And then for my third partition, I'm going to have my midpoint right there and draw my rectangles. These are what my MRAM rectangles look like. Now notice the wording of this said, use MRAM to partition the time into 3 subintervals. 3 subintervals means 3 rectangles. Okay, now if we wanted to find the area of the rectangles, or estimate the area using MRAM, we would actually have to find f of 0.5, f of 1.5, because these are the midpoints. 1.5 is here, and then 2.5, we'd have to find that. So let's go ahead and do that. Let's plug those in and find those values. So here are my y values, and again, the idea is length times width, right? So when I look at this first blue rectangle here, 0.5 is the x value, f of 0.5 is 1.5. So the idea here is that this side, because I'm going up to here, at this height right here, this distance is 1, right? So the idea is it's the width of the interval. Just because 0.5 is my midpoint, it's still 1 unit, 1 hour, 1 whatever wide. But the height is going to be that f of 0.5. 1.5 is the height. So the area of this blue rectangle is base times width. 1.5 times 1, or 1.5. So we already found one area, it is 1.5. Now to find the red area, we're going to be using the height here, which we found the y value, f of 1.5 is 5.5. Now the base is still 1, right? Because the base is the distance between the 1 and the 2. So here, my area of my rectangle is 5.5 times 1, or 5.5. So right now we have 2 areas, 2 rectangles. Now we're ready to find the third one, and then we just add them together. So f of 2.5 is 13.5. So when we go back up here to this purple rectangle, this height here is 13.5. That's the f of 2.5. This is my midpoint. So 13.5 times 1, the width is still 1, right, is just 13.5. So using MRAM to approximate, we found the areas of the 3 rectangles, and then we add them together. 1.5 plus 5.5 plus 13.5. And that gets us, what, 6, 7, 20.5 as our approximation. That's how we do an MRAM problem. Now what we're going to do is we're going to do an LRAM problem. We're going to use the same function, and LRAM should be just a little bit quicker since we don't have to find all those midpoints, and I've already written them down up here. But let's draw our LRAM rectangles. So our LRAM rectangles will look like this. I'm still going to partition the same way. I'm going to draw my lines down at each interval. Here are my 3 subintervals, 1, 2, 3. LRAM just starts on the left. So here, here, and here. These are my 3 rectangles. Now, the height of the first rectangle is this value 1, because that's my other point. So I have 1, 3, 2, 9, 3, 19, and I forgot to write down 0, 1. So the height here is 1, the width is 1, so the area is 1 times 1, or 1. Here, the height of the second rectangle, 1, 3, is 3. The width is 1, so 3 times 1 is 3. So far, my areas are 1 plus 3. And then my last rectangle is going to use the left side as its height. So f of 2 is 9. The width is 1. 9 times 1 is 9. So here we have an estimate of 13. Very different from our MRAM estimate of 20. So you can see there's quite a bit of variation when you only have 3 subintervals. So what does RRAM look like? Let's go ahead and use RRAM. RRAM uses the right side of the interval. So I'm going to do it the same way. I'm going to still drop these lines down. Boom, boom, boom. There's my 3 partitions. But this time when I draw my rectangle, I'm going to use the right side. So this one's going to be way over. Look at that. Those rectangles are so much bigger, so much taller than the curve. Again, for each of these, the width is 1, but the height is what's different. So for the little triangle, the height is at 1. So it's the point 1, 3 up there. So the height here is 3. So 1 times 3 is an area of 3. For the second triangle, I'm going to use the y value at x equals 2. So this second middle value has a height of 9, so 9 times 1 is an area of 9. And then last but not least, this one has a height of 19. 19 times 1 is 19. So 19 plus 12 is like way more than 20.5. 31. So what a difference between the 3 approximation methods when we really sit down and look at them. This is how we would do this with a curve. 3 to 4 partitions by hand is not unacceptable. Usually that's kind of where we'll be with drawing, the value, drawing the curve, and then sketching the rectangles. Now, what do you need to show on your work? You need to show your rectangles. You need to find the y values. Is it the left side or the right side? That's your approximation. And then after that, you'll need to tabulate and calculate each area and add it up by hand. Now, this is going to be part 1 of a 2-part video here for LRAM, RRAM, and MRAM. In part 2, we're going to talk about what happens when you have tabular data or data in a table, because how you deal with MRAM, RRAM, and LRAM in a table is very different from how you would handle it on a graph. But for now, this is a good introduction into slicing a curve and our very first peek at the most basic of slicing techniques, LRAM, RRAM, and MRAM. And if this is your first time trying this, just remember it will get easier, it'll get better. The more practice you do, the better you get at these things. So as always, my encouragement to you is to stick with it. You can do this. You've got this.